Hello. In this video, we will continue our discussion of Kasumu's book on Introduction to Stochastic Processes, Section 2.2. First of all, I would like to make a correction to the first video. In exercise 1E, let me make this larger, I mentioned probability of xtn given x0. In the previous video, I had probability of xtn equal 1 given x0 equal 1. This was a mistake. I want probability of xtn equals 0 given x0 equals 0. In fact, these two values are the same, but it's easier to put the 0 here because you have the 0 from problem 1D. So with this exercise as written here, you can use your result from 1D to prove 1E. Okay? So briefly to review the previous video, we introduced a Markov process with continuous time and discrete states. The continuous time was implemented by making the transitions occur not at integers, but at small time steps. So here we have the small time steps. In a unit time, we have capital N time steps. So that means capital N transitions. Each transition looks like this. It goes from a state either to the next state or a state to itself. If I am to end up in state K at time n plus 1, either the process was in state K the previous time or the process was in state K minus 1. Let's continue the discussion. Now, we found in exercise 1E that the limit, as n goes to infinity, of the probability that xtn equals 0, given x0 equals 0, is e to the minus lambda t. This was using the discrete Markov chain notation, where xtn is the value of x after tn time steps. Now remember, tn time steps corresponds to tn steps of time interval 1 over n. So in fact, this corresponds to time t. So in our new notation, we are going to write this as the probability that xt equals 0 given x0 equals 0. For our continuous time Markov process, we don't refer to the number of steps. We only refer to the time. Time t corresponds to tn steps in the process. Okay? So we want to write this limit in this way. So we would like an expression for the probability that xt equals n given x0 equals 0. Remember, xt can move from 0 to 1 to 2 to 3 and so on. The states in this process are discrete. Let's see what we can do to find this expression. All right. Now, from the Markov chain matrix, which I hope you have been able to construct, we have that the probability that x of t plus dt equals n, given x of t equals n, is 1 minus lambda times dt. This corresponds to this second possibility here. Remember, we're associating 1 over n with a small time interval dt. Okay? Similarly, the probability that x of t plus dt equals n given x of t equals n minus 1 is lambda times dt. So the probability of this transition from, well, let's see, where did I write it? From k minus 1 to k, the probability of a transition to the next state is lambda over n. And remember, 1 over n corresponds to dt. All right. Now, there is no other transition possible if at time t plus dt, the process is in state n, then at time t, the process must have been either in state n or state n minus 1. It could not have come from another state. So there are only two possibilities for xt. Either xt was n or xt was n minus 1. In case xt was n, the transition probability is 1 minus lambda dt. So the probability that the chain started in n and moved to n, that is, remained in n, would be equal to this probability, the probability that the chain was in state n at time t, times this transition probability. So this quantity here is equal to the probability that xt is equal to n and xt plus delta t is equal to n. So what about this probability here? Well, this probability is the probability that the chain or the process was in state n minus 1 at time t times the probability that the process moved from n minus 1 to n during the time interval dt. So this is the probability that x of t is equal to n minus 1 and x of t plus dt is equal to n. Okay? Now, there's only two ways that the process can be in state n at time t plus dt. Either it was in state n at time t, or it was in state n minus 1 at time t. These two possibilities here, this one and this one, express the only two possibilities for this event. Okay. So that's why we have equality here. These are disjoint events which together make up this event here. Okay. All right, now, instead of writing probability of x t equal n, we're just going to write Pn of t. So we should understand when you see Pn of t, that means the probability that the Markov process is in state n. Okay? So we have this equation we can rearrange. You can see we have probability x of t plus dt here, and here we have two values for probability of x of t. And we can get this equation down here. Remember, Pn of t plus dt, this value here, is simply the same thing as here. The book uses a delta. I'm using a d. It means the same thing. Okay? So this quantity here is the same as this quantity here. This quantity here is the same as this quantity here. Okay? Now, to get from this equation up here to this equation down here, you need to break up this term 1 minus lambda dt. But this is simply some algebra operations. You should be able to do that yourself. The reason for this last term, O of delta t over delta t, is because we are going from a discrete to a continuous process. In fact, the book uses the wrong notation. This should be a small o and not a large O. Small o of delta t means a number that is small compared to delta t. In fact, in our discrete approximation, this equation is exact without this term. So you should just think of this extra term as something small that can be ignored in the limit as delta t goes to 0. Okay? So if we take limits of this expression as delta t goes to 0, this left-hand side should be familiar as a derivative. Right? You have some function evaluated at t plus delta t minus the same function evaluated at t divided by delta t. That's the standard definition of derivative. And then these two terms go over the same way. So we have a differential equation. Now, in fact, this is a vector differential equation. Why is that? Because we have p of t for each value of n, p0 of t, p1 of t, and so on. So this is not just one differential equation. We can arrange it in a vector format. Right? So we want to treat the vector as a single quantity. We can use a very elegant method and identify this vector with a polynomial in the variable z. In fact, every polynomial can be considered as a vector. If you have had linear algebra, then you may know that polynomials form a vector space. So we can identify this vector p of t, p0 of t, p1 of t, and so on with this polynomial, p0 of t plus p1 of t times z plus p2 of t times z squared plus ... and so on. Now I could have used the variable x instead of the variable z. It really doesn't matter. I'm only following the notation of the book. So in fact, I can consider this entire polynomial as a function of t and z. The book calls this g of t comma z, as right here, g of t comma z. All right? So I want to change this set of equations into a single equation involving g of t comma z. The way I do that is I multiply the nth equation here by z to the n and sum. Now if I multiply this term by z to the n and sum, I'll get minus lambda times g of tz. If I multiply this term by z to the n and sum, I'll get the time derivative of g. If I multiply this term by z and sum, you can see that what you get in fact is equal to z times the polynomial g. Okay? So these three terms here come from these three terms here when you multiply these terms by z to the n and then sum. Okay? Now this is very nice. Instead of an infinite sequence of equations, we have a single equation involving a polynomial in two variables. Now if you know something about differential equations, you know you need to have initial conditions as well. We are starting the process in the state 0. That means that p0 of 0 is equal to 1. I'm sorry, this is not clear. This should be a 0 here. p0 of 0 is equal to 1. The process is not in any other state, so Pn of 0 equals 0 for all other values of n. Now if we multiply these equations here by z to the n and sum. In other words, I multiply this equation for n equals 1 by z, the equation for n equals 2 by z squared, and so on. Then I will simply get that the value of g of z0 is equal to 1. Now, this differential equation can be solved using standard methods. What do we have here? Let me write it again so it's more clear. We have the derivative of g of z comma t with respect to t is equal to, well, I'm going to write these two terms together. I have a minus lambda, and then I have plus lambda z times g of z comma t. Okay. So in this equation, we may consider t as the variable, and I can consider z as a parameter. Okay. Since z is a parameter, I may consider this value as a constant because it does not depend on t. It's independent of t. So this equation has the form, since I'm only dealing with one variable, instead of writing partial with respect to t, I'll just write it as a derivative. And this is equal to some constant, which I can call c, times g. I hope this is a familiar differential equation to you. The way to solve this is you cross multiply. You can write this as 1 over g dg equal to c dt, and integrate both sides. Log of g equals ct plus some arbitrary constant. And I can take the exponential of both sides of this equation. And that will give me g is equal to, I can write this as e to the k times e to the ct. E to the k is a constant, so that's just a times e to the ct. Now what was c? C was the value of the constant here minus lambda plus lambda z. So that means g equals some constant a times e to the minus lambda plus lambda z. Now, you can find the value of a using the initial conditions. The initial conditions were up here. These conditions here, p of 0 of 0 equals 1, pn of 0 equals 0. And that means that the value of g is equal to 1 at 0 when t equals 0. So if you plug in t equals 0, that means g equals a. So that gives me that a is equal to 1. Okay. Now I can take the power series expansion of g, gives me the coefficients of the powers of z. And these coefficients are the values of Pn. And you can follow that argument in your book. It's at the bottom of page 63. Okay, let me stop here and we'll do one more video to complete this section.